All right, so now I'm going to talk about Hamiltonian systems. Okay, so let's say we have H, which is a Hamiltonian. And so usually the Hamiltonian depends on P and Q, okay, where P is some sort of generalized momentum, and Q is a generalized position. Okay, so the Hamiltonian is a scalar valued function on what's called the cotangent bundle. Which has local coordinates Q and P on that. Okay, and it's a map from TQ to the rails. Okay, and then given the Hamiltonian, you have what are called Hamilton's equations. Okay, which say that Q dot is equal to dH dP, and then P dot is equal to minus dH dQ. Okay, and let's look at an example of something like this. All right, so oftentimes the Hamiltonian is an energy. So let's look at a simple example, H, which is 1/2 P transpose M inverse P, where M is some sort of mass matrix, and then there's a potential energy which I call V of Q. Okay, so if you have that and you substitute it into Hamilton's equations, you get that Q dot is equal to dH dP, right, which is equal to basically just M inverse P. All right, another way of sort of thinking about this is that in the usual mechanics case, it's like, say, with particles, then the momentum is the mass times the velocity, right? So that's consistent with that. And then the other equation is that P dot is minus dH dQ, right, which is minus dV dQ. All right, and then this is, of course, the time rate of change of the momentum. Right, so this says that the time rate of change of the momentum is equal to the negative of the gradient of the potential respective position. And so in, again, a usual mechanics situation, it's like the force, it's like due to a potential term, right, is negative of the gradient of that potential. So this is basically a statement in Newton's second law, which says that the time rate of change of momentum is equal to the force applied to the system. Okay, all right. So, so let's look at some conservation properties of Hamilton's equations. So the first thing is that the Hamiltonian is a constant of motion. Right, remains constant. Along the solution trajectory. Okay, and so let's just prove that. Okay, so the time rate of change of the Hamiltonian, Q of t, P of t, right, is of course nothing more than the partial of the Hamiltonian in respect to position times the time rate of change of position plus the partial of the Hamiltonian in respect to momentum times the time rate of change of momentum. Okay, so then we can substitute Hamilton's equations into this. You get dH dQ, Q dot is equal to dH dP, right? dH dP plus dH dP, and then P dot is minus dH dQ. Right, so it's easy to convince yourself that those two terms cancel, and you just have that the Hamiltonian is a constant of the flow. Okay, So it turns out that that's not the only invariant, if you will. It's like of a Hamiltonian system, and it's not necessarily even the most important. And there's sort of a deeper property of Hamiltonian systems, which is preserved. Okay, and that's what is called symplecticity. And maybe let's just write down the equations here. Q dot is dH dP. P dot is minus dH dQ. Okay. All right. So there's this idea, what is called symplecticity. Okay. So one manifestation of symplecticity is the observation that if you have a Hamiltonian system with one position variable and one momentum variable, right, sort of a 1 + 1 dimensional system, then the area it's of the phase space is preserved by the flow. All right. So the observation. So one observes that in a sort of one position, one momentum system, one momentum Hamiltonian system, the phase area is preserved by the flow, by the Hamiltonian flow. Okay, but you know, one natural question is asked: well, what happens sort of in higher dimensional Hamiltonian systems? So it turns out that the generalization of this is not that the volume is preserved, even though it is true that volume is preserved for a high-dimensional Hamiltonian system, but there's sort of a more subtle sort of invariant, which is what is referred to as symplecticity. Okay, so let's just say the following. So a map, okay. So a map. Let's say phi, okay, from omega to R2D, where omega is contained in R2D, right, is symplectic. Okay, if the following is true, if the essentially the linearization of that map, which we call phi, capital Phi, okay, transpose, let's see, J phi y is equal to J, right, where this thing is equal to the linearization of the map at the point y respect to y. Okay, so this is, yeah, so that's the linearization, and J is equal to this 2D by 2D matrix, okay, which is 0, the identity, minus the identity, and 0. Okay, so each of these things are D by D matrices, if you will. And you can, so this can be interpreted as the preservation of the sum of signed sort of areas. And you can ask, what would I mean by signed areas? It's like, okay, because if you have sort of, you know, these position momentum variables, then you can have matched position and momenta. So you have the sum of the signed areas on sort of the QI, PI sort of basically planes, right? So so you have a 2D dimensional space. It's like, and you have these matched planes. It's like which have to do with the matched positions and momenta, and you take some phase volume, you project it onto this match position momentum space, you compute the signed area, and you sum it all up. And then this idea of symplecticity is that that sum of the signed areas, it's like it's constant along the flow. Okay. And I should say that in particular, one consequence of this is that the Hamiltonian flow, it's like, or which is symplectic, okay, we'll show it's symplectic, right, is also volume preserving, okay? So this sort of implies, if you will, volume preservation. But I should say that in general, that's a stronger condition than volume preservation. So, so there are examples of maps which are not symplectic, but which nevertheless preserve volume. Okay, and it's only in this sort of 1+1 case, where it's one position and one momentum, that the this notion of sum of signed areas, it's like, and volume preservation agree, because in that degenerate case, it's like you just have one signed area, which is exactly the area form, and those two notions agree with each other. But in higher dimensional problems, volume preservation is a weaker condition than symplecticity. Okay.